Yeah, so we have seen about the hybrid pi model of a bipolar junction transistor, and now we can see how we can analyze the high frequency and low frequency signal or the frequency response of a bipolar junction transistor using this hybrid pi model, right? So for that, consider a potential divider bias bipolar junction transistor common emitter amplifier, right? So yeah, I have my VCC, then RC transistor. This is an NPN transistor. Then RE emitter resistance, which is grounded, and then this emitter resistance will have a bypass capacitor CE, and then I have my potential divider here. This be R1 and R2. R1, R2, and then I have my AC source with the internal resistance. So this be VS and RS, or the source resistance. Then I will measure my V out from here. Of course, we will have an input filtering capacitor here, right, from the circuit. So this will be C in, and may have an output filtering capacitor at this terminal as well, which will be my C out, right? So now, first of all, let's see how we can draw a hybrid pi or hybrid pi equivalent circuit of this common emitter transistor amplifier. Right, so we have three rules. First thing, we need to short circuit any DC current sources, and all the capacitors should be short circuited. And if you have any inductance, those should be removed from the circuit, right? Those should be removed. Capacitors should be short circuited and impedance should be open circuited. Any DC current sources should be short circuited and DC current sources should be removed from the circuit, right? So we'll do it one by one. First of all, we'll substitute the transistor with the hybrid equivalent model, right? So we know that, yeah, so I'll draw the equivalent circuit first, right? So I have my, which is my Rx, R pi, and then capacitor C pi. Here I have C mu, and of course we can neglect the R mu, right? The parallel capacitance introduced by base collector junction, right? That can be neglected due to its very high value. And then we'll have my transconductance Gm into V pi. Yeah, my V pi is actually the voltage across these 2 points. Right, so this will be my V pi. So Gm into V pi, and this will be my collector. This is my emitter, and this one is my base terminal. Right, so this is the complete hybrid pi model of a bipolar junction transistor. Now we'll do the external connections now, right? So first of all, as I said earlier, all the capacitors should be short circuited, right? So this capacitor will be removed from the circuit, and this one, and by short circuiting the bypass capacitor CE, RE, will be removed from the circuit as well. Due to the zero resistive parallel path, we can remove RE from the circuit. Next thing, we don't have any DC current sources or inductances, but we have a DC voltage source, and that should be grounded. Right, so if this is grounded, I would simply say I can remove the wire and then I'll put a ground here as well. Right, so this one ground, ground, ground. Right, so this, now we'll translate this circuit into the model. Right, so this is actually inside the transistor, right, the equivalent circuit of the transistor, and now we'll connect the external components in it. Right, so this is the transistor, what we have here. Right, so this is my collector, emitter and base, which is collector, emitter and base. Now let me connect the external components. Right, so we have RC and that is grounded. Right, from collector, RC and grounded. Am I right? So from collector, I can have my RC and that is grounded. Right, RC. Right. Similarly, look at here, emitter is directly connected to ground. Oh, that is short circuited. Right. So emitter, I could put it somewhere here, right, which is short circuited, directly grounded. And then I have base. Look at here, if this is ground, I could draw a separate ground, something like this. So from base, I have R1, right, base R1 ground, base R2 ground. Or simply by folding this one upside down, I can say that at base I have a parallel combination of resistance, which is R1 and R2, right, which is R1 parallel R2 from base to ground. Right, so I could write this as from base to ground. I have my R1 parallel R2, or I could connect this one together, right, since they have grounded, I can have a connection there, right. Similarly, from base, RS and VS, and that one is grounded as well, right. So I can simply draw RS, this is my source VS, and that is grounded as well. Right, so this is my complete equivalent circuit. Now look at here, yeah, the whole emitter line is grounded, so I could extend this one something like this. Oh, I can pull this one up, right, I can pull this one up, right, so I can simply draw a line without these things, right, so that is grounded. And again, this is ground and RC, which is grounded again. So I can connect this one from, since they are equipotential points, or ground, ground, I can simply fold this one to E, right? So what I can do is I can remove this one, and of course that can be extended somewhere, something like this. And then this will be my RC. So finally, right, again, since Rx is a very small value, right, when compared to R1 parallel R2, since we are using them as the biasing resistors, potential dividers, R1 parallel R2 will be a much bigger value, right. So simply you can neglect them from the circuit, right, since you have a very high value resistance in parallel, I can assume that there are no current flow through that, and simply it can be removed from the circuit. Right, now I'll redraw this circuit. Right, so I have right, so this will be my RS and VS. Right, so I have a single line, which is emitter, right, and then of course this is neglected, so I have my Rx and then I have my R pi, C pi, and then C mu, and also I have my Gm into V pi and RC. So this is my final circuit, right? Final equivalent circuit, hybrid pi equivalent circuit of a potential divider biased common emitter transistor amplifier. Now we can do the analysis. Of course, I need to mark V pi, right? So V pi, the voltage across R pi and C pi, right? So this will be V pi. Right, this will be V pi. So all these things is inside the transistor, and based on the equivalent circuit, only Rs, Vs comes to the input of the transistor amplifier, and Rc comes at the output. So I could mark this one as my V out. Right, I can mark this one as V out, and this will be my I out. Right, I out. Right, so if I mark this I out something like this, so I can write my V out equals, right, since the current is flowing from here to here, that should be minus, right? So here you have lowest, and here you should have high potential, right? So right, or in other words, if you put the I out in the other way around, this will be V out, then I out will be minus Gm into V pi into Rc, right? So I can put it as minus Gm into V pi into Rc, right? So V out will be minus Gm into V pi into Rc, right? So here, the first thing we need to do is, before going for further analysis, we have C mu here, right, which is a bit difficult to continue the derivation. So simply what we can do is, we can apply Miller's theorem to divide the capacitor in the output and, sorry, in the input side and the output side as well, right? So first, we'll divide the capacitor, right, using Miller's theorem. So we have seen that capacitor can be divided. Yes, the input side will be 1 minus AV times C mu, right? So I can simply remove this one, and then one component will be in the input side and one component will be in the output side, right? So what we can do is, I'll redraw the circuit again with two components of C mu, right, with two components of C mu. R pi, C pi, Rx, and then of course I have my C1, right? Let this be C1, and then Gm into V pi C2, and finally I have my Rc, right? Of course, here I have my Rs and then Vs, right? This R could be, Rs could be the internal resistance of the AC source, or it could be a an external resistor connected to that one, right? If the internal resistance of your source is 0, simply you can short circuit it, right? So as I said earlier, we can apply Miller's theorem to a closed circuit, right? So as we seen earlier, right? So we can see that, yeah, here we are going to apply Miller's theorem in this circuit, right? In this uh, region, right? I would say the input voltage is V pi and the output voltage is minus Gm into Rc into V pi. So simply my gain will be, right? So I would say A, right? I would say my A equals minus Gm into V pi into Rc divided by V pi. So V pi will get cancelled. Then A will be minus Gm into Rc. Right now, using Miller's theorem, this C mu can come, or C1 can be written as C mu into 1 minus gain, so minus into minus becomes plus, Gm into Rc, and C2 can be written as C mu into 1 minus 1 plus 1 over 1 plus A, right? Gm into Rc, right? Sorry, 1 over 1 plus 1 over 1 minus 1 plus 1 over 1 by A, right? So this becomes 1 over 1 by A, right? So which is, since it is very smaller value, right? When compared to Rc, this will be, C mu will be a very small value, but that when it multiplied by Gm into Rc, that will be a bigger value, and then 1 minus 1 over Gm into Rc, right? Yes. So this we can neglect it, of course. 1 minus 1 over Rc, so this will become 1 plus 1 by Gm into Rc, right? So 1 by Gm into Rc, we can neglect this one, or if it is very big, this could be 0. So C2 will be directly C mu, right? Which is about, in terms of picofarads, right? Will be about, yeah, practically that's about picofarads. So simply we can neglect, when compared to Rc, the impedance of Rc, the parallel capacitance offers a very low impedance. So that can be neglected, but since Gm into Rc is very big, right? Gm into Rc is very big. Rc is in terms of kilo ohms, and when we have a bigger value, C mu will be multiplied with that, and that comes in parallel to C pi, right? So when we have two parallel capacitors, we can substitute that by a single capacitor, which is Ct, right? So Ct can be written as C pi plus C mu into 1 plus Gm into Rc. So the whole circuit can be simplified into another circuit, right? Something like this, right? So there are no capacitance here. These two capacitance can be substituted by a single capacitance, which is Ct, right? So Vs, Rs, Rx, R pi, and now I have Ct instead of C pi, right? So this is open now, right? So I have my Gm into V pi, finally have Rc, right? So this is my final circuit, right? So this will be my current, and Rc, Ct, R pi, Rs, and Rx. Now will apply simple circuit rules to estimate or to define the frequency response of this amplifier, right? So this will be the output voltage V out. Right, so now here similarly I can write my V out as minus GM into V pi into RC, right? Okay, right, so here I can write my V out equals to minus GM into R pi, sorry, V pi into RC. GM into V pi into RC. Right? Now, we'll determine, this is V pi, right? This is our V pi, right? To go for my AV, which is voltage gain, right? Voltage gain. What I need is V out by Vs, right? V out by Vs. But here we have V pi. But from this circuit, we simply determine V pi in terms of Vs, Rs, Rx, and these two. Right? Vs, Rs, Rx, and these two. Or in simple words, see, look at here, I am removing this Vs, and then these two comes in series, and R pi Ct becomes parallel. Right? To determine V pi, okay, I can consider this as a simple potential divider, or I can draw this one something like this, right? So this will be Rs plus Rx, which is in series, right? The combination of these two. Now I have R pi parallel Ct, R pi parallel Ct. Right, the whole voltage across the input side will be Vs, am I right? So this will be Vs, and what I need is, I need to find out what is my V pi, which is across this one, right? So this will be my V phi, right? So if I calculate V phi in terms of Vs, just substitute that one here, I can easily calculate V out. Right, so this is a simple potential divider, right? So I may substitute C pi into this one as a impedance Z, right? So let my Z equals, right? So which is 1 over Z equals Z equals R1 R2 by R1 plus R2, right? So simply I can write it as R1 R2, so R pi into 1 over j omega Ct divided by R phi plus 1 over j omega Ct. Right? R pi plus 1 over j omega Ct, which is my Z. Right? Again, I am going to apply this one in this equation, right? Okay, let me consider this as Z, right? The whole thing as Z, right? Whole thing as Z. So my V pi will be, right? So I can write my V pi as, right? So V pi will be Z by this one plus this one into Vs, right? Using potential divider or potential divider equation, right? We have seen it when we have two resistors R1 and R2 or the V2 will be R2 divided by R1 plus R2 into PS, right? That is the simple way is to calculate the current and then apply it for potential, right? So I can write my V pi as Z divided by Rs plus Rx plus Z into Vs, right? So I'll substitute this one and then I can bring my Vs the other side. So I can simply write my V out is equal to, so minus Gm into Rc into, right, Z into, right, so Vs will be there. I'll just bring it to the other side, right? Vs, so there is no Vs there. Rs plus Rx plus Z. Now substitute Z with this, right? Substitute Z with this. So simply we can uh, um, okay, I'll do it. We'll see how we can simplify this one as well. Right, so this I can substitute by AB, right? AB is equal to minus Gm into Rc into, instead of that we are going to put this one, right? So instead of that will be R pi into 1 over j omega Ct, right? The total capacitance divided by Rs plus Rx plus, oh sorry, divided by R pi plus 1 over j omega Ct. Sorry for that. So here I'll have plus R pi into 1 over j omega Ct. Okay. In simple, what we can do is, okay, so my AV, right? V out by Vs will be AV. So divide numerator and denominator by Z. So I can simply write this as minus Gm into Rc divided by, so 1 plus Rs plus Rx into 1 over Z, right? So 1 over Z. So 1 over Z will be inverse of this one. Or simply I can write 1 over Z equals, right, using parallel resistance, 1 over Z equals 1 over R pi plus 1 over j omega, 1 over j omega C, which becomes j omega C. Right, so I can rewrite this one as AB into minus Gm into Rc divided by 1 plus Rs plus Rx into 1 over Z can be written as 1 over R pi plus j omega Ct, right? J omega Ct. t. So I can simply separate this one into real numbers and imaginary numbers, right? Since we have r pi 1 over r pi component, and then j omega ct component, I can simply divide this one into real and imaginary. So I can rewrite this as minus gm into rc divided by 1 plus, so this one becomes, so 1 over r pi into rs plus rx plus j omega ct into rs plus rx. Right, now multiply both numerator and denominator with r pi, so we can remove this one. So this becomes minus gm into rc into r pi divided by, so we can multiply this one, so the whole term becomes, when we are multiplying this, so r pi plus rx plus rs into, so when we are multiplying this, it becomes plus j omega ct into r pi into rs plus rx, right? So this will be our equation, and then now this is in terms of, so we can simply change this equation in the form of AV mid by 1 plus, right? So j omega c of j omega by j omega dash and omega h, right? J omega h. We can convert it into the form of a frequency response equation. So as to make this one the real number as 1, again we can divide the whole terms by 1 over gm into r pi over rc divided by, we can divide the whole term into 1 over r pi plus rx plus rs. So simply, so the whole terms becomes minus gm into rc into r pi divided by r pi plus rx plus rs were 1 plus j omega ct r pi into rs plus rx divided by r pi plus rx plus rs. Right, so now this equation is in the form of, right, so this is in the form of, we can rewrite this as AV equals AV mid over, AV mid means mid-band gain, right? AV mid stands for mid-band gain, right? Over 1 plus j into omega by omega h, right? So this stands for the upper cutoff frequency. Omega h is the upper cutoff frequency. So now from this equation, we can say that AV mid is the whole term, right? This is the whole term, right? So I can simply write my AV mid equals Gm into Rc into R pi divided by R pi plus Rx plus R, right? So that will be our mid-band gain, right? And then now omega h. So we have j omega, right? So j omega is this one. So j omega is this one. The whole term, the rest of the term is equal to 1 over omega h. Am I right? So the whole term is equal to 1 over omega h. So I can simply write my omega h equals, so the whole term is 1 over omega h means, so the omega h will be, these terms will go up and then that will come down. So simply I can write it as omega h equals r phi plus rx plus rs divided by ct into r phi into rs plus rx, so rx, small rx, right? So yeah, this will be rx. Don't confuse it. Right, so this will be my upper cutoff frequency. So whenever if I draw the frequency response of from an emitter amplifier at high frequencies, so I have a constant midband gain, then it started reducing after a certain frequency, and my omega h will be, right, omega h will be, right, so if this is AV mid, this will be AV mid phi root 2, right? So which means eventually if you have frequency above omega h, your gain will be much lower than AV mid, right? So now, so this is the high frequency response or high frequency, the problems arising when you are applying a transistor at very high frequencies. Now, let's see how the transistor behaves at low frequencies, right? Right. So at low frequencies, of course, low frequencies, omega will be much lower, right? Omega will be much lower. So 1 over j omega ch. And so these capacitance, the capacitance produced by the transistor itself due to the depletion region of base collector and base emitter junctions, right? Since they are very low values, and again the frequency will be much lower, so 1 over j omega c will be again much lower, so they can be removed from the circuit. When the transistor operates at low frequencies, this input capacitance C in comes into action, right? The C in is going to work as a filter when it comes to a low frequency, right? So now we can redraw the same hybrid pi model of the transistor at low frequencies, something like this, right? So we have, so we can simply neglect the capacitance or the internal capacitance comes from the equivalent circuit, right? These things can be neglected, but we are going to have our C in at this point that is going to act as a filter, right? That is going to work as a filter which is going to limit the input frequency range, right? So we limit the frequency response at low frequencies. Right, so with this C in, now we can redraw the equivalent circuit, right? So there will be no capacitors, but only with this C in, the final equivalent circuit will be, of course, Rs C in Rx, and then only here we will have that we are phi, right? R phi, and then C phi or CT will be removed as it is a very smaller values at low frequencies when omega is lower, right? So this will be Vs. Then finally we have Gm into V pi, right? So V pi is the voltage across R pi, and then of course our RC. This will be V out. Right, okay, as we did previously. So here we are going to have, this is my V pi, right? So this will be my V pi. So earlier, as we did earlier, so V out will be minus Gm into RC into V pi, and then our gain AV equals V out divided by Vs, right? So we have to calculate V pi in terms of Vs, and it is simple. So now we have again a potential divider, but now the capacitor comes in series with these resistance, right? So I can redraw the potential divider something like this, right? So I can redraw, or simply by pulling this one up, I can redraw the potential divider something like this, since Rx and Rs in series. So these two, Rs plus Rx, they are in series, and then I have my C in, right? And then here comes the R pi, right? So this whole voltage is actually Vs. Right, this Vs, and then this will be my V pi, right? So I can write V pi in terms of Vs using the potential divider equation, right? Potential divider equation, simply, so V pi equals R1 over R1 plus R2 divided by, sorry, R1 divided by R1 plus R2. So let this be Z, which is equal to R plus J omega C. Or I can simply write this one as Rs plus Rx plus 1 over J omega C in. Right? 1 over J omega C in. So I can write my V pi now. Right? So V pi is equal to R pi divided by R pi plus Rx plus Rs plus 1 over J omega C in into Vs, right? So now I'll substitute the whole equation here, right? So I can substitute, instead of V pi, I can put the whole thing there, and then I can bring Vs the other side, right? So now let's see. So now my V out is equal to minus Gm into Rc into, of course, this R pi will be there. So V R pi and Vs will be in the top. So R pi and Vs, I can bring it to the other side directly, right? Vs equals 1 over the whole term, right? So this Rx plus R pi plus Rs. So 1 over j becomes minus j, right? 1 over j becomes minus j. So minus j into 1 over omega C in. Again, to make this one as minus omega, make it into 1 minus omega C. So I can divide the whole term. To make this one 1, right? I can divide the whole thing by the equation. So I can rewrite my AV, right? Which is V out by Vs, right? V equals minus Gm into Rc into R pi divided by Rx plus R pi plus Rs divided by 1 minus, right? The whole thing will be divided, right? J into 1 over omega C in into R phi plus Rx plus Rs. Right? So now this is in the form of AB mid divided by 1 minus J into omega L over omega, right? Here comes the lower cutoff frequency. So now I can write my AV mid as this one, which is same as we had in our low frequency and high frequency analysis as well, right? Gm minus Gm into Rc into R pi. Right, so now AV mid will be minus Gm into Rc into R pi by Rx plus R pi plus Rs. Where, of course, last class some of you have asked a question. This minus indicates a 180-degree phase shift. Right, this minus indicates a 180-degree phase shift. Right, which is we'll see. We have already seen it in our common emitter transistor amplifiers, right? So now here the omega L, right? So J omega is here. So the whole rest of the thing will be omega L. So I can say that I can simply write my omega L as 1 over C in into R pi plus Rx plus Rs. Right, so in our high frequency response we have seen something like this. So whenever the transistor comes into low frequencies, it's also going to have cutoff frequency which is omega L, right? So this cutoff action is due to the filtering capacitors, and the upper cutoff frequency or upper filtering action is due to the internal capacitance of a transistor, which are produced by the depletion region of the base collector and base emitter junctions, right? So now from this, of course, we have derived everything, right? Yeah, so this will be minus, right? There should be a minus, right? So this is same as low frequency analysis. Then we have omega H, which is this one, and omega L, which is this one, right? So omega is actually angular frequency. If you want to convert this into F, just as you know, we know that omega equals 2 pi F, right? If you want to convert F, omega into F, and then just divide the whole term by 2 pi, you will get omega L and omega H in hertz, right? This will be angular frequency, right? So now we can simply say that within this region, your transistor amplifier have a gain of at least AV by root 2, AV mid by root 2, right? And we call this region as bandwidth, right? Which is equal to omega H minus omega L, right? Omega H minus omega L. Ideally, for an ideal amplifier, the bandwidth should be infinity, right? For example, it should give you, if it is an ideal amplifier, for 0 hertz or infinity hertz, you should have a same frequency. But that is not possible when it comes to transistor amplifiers due to the internal capacitance and the input filtering capacitance you are using, right? So that's all about common emitter transistor amplifier, and then in our next class we can see about common collector transistor amplifiers.